Video, we're going to briefly talk about some topological theorems for subspaces of the real numbers in n dimensions with the usual topology. These are also called Euclidean spaces. So that's where we've got the real numbers in n dimensions as a metric space given by the standard metric where the distance between 2 points is the square root of the sum of the squared differences between their coordinates. So, if we're talking about R2, for example, and we've got 2 points, it's just the standard distance, the length of the straight line between the 2 points, X and Y. So a couple subsets of, or subspaces of Rn that we'll commonly use are S to the nth power. This is basically like a hollow sphere or circle as a subset or a subspace of R to the n plus 1. So if we're looking at S1, that's a subspace of R2, the plane. And so it's just the circle not filled in, just the circle with no interior. That's S1. S2 is the hollow sphere as a subspace of R3, of the real numbers in 3 dimensions. And we can keep going, and S to the n is a subspace of R to the n plus 1. It's going to be the set of points at distance 1 from the origin. It's harder to draw, but we can certainly think about it conceptually. So as an example, if we look at the half-open interval that goes from 0 to 2 pi, and we think about a function mapping this half-open interval to S1, one kind of obvious function we could use is to take the point on the interval, say pi, and that would be mapped to its angle pi on the unit circle. So this is an angle of pi. So this is clearly going to be a continuous function, and it's also going to be a bijection. So for every point here, there is a point here. It is not, however, a homeomorphism. So it's not a homeomorphism because F inverse is not continuous. F inverse is not continuous because there are sets that are open in this subspace 0 to 2 pi that are not open, or such that their image F of that is not open in S1. So for example, the set 0 to pi over 4 as a half-open interval, that's equal to, let's say, negative pi over 4 to pi over 4 intersected with our subspace 0 to 2 pi. So this is open, and therefore this intersection 0 to pi over 4 is open in the subspace given by R. Whereas if we look at this F of this interval from 0 to pi over 4, this is not going to be open in S1, because if we think about the subspace S1 and think about this half-open interval, this set, this is not open. It is not equal to any intersection of an open set in R2 intersected with S1. So it's a continuous function that is not that is also a bijection, but is not a homeomorphism. One thing that could have clued us into this not being a homeomorphism is that we have this S1, this space has a hole in it, whereas this space has no hole. It's just a straight line with no hole in it. And in general, two spaces of Rn can only be homeomorphic, or two subspaces of Rn can only be homeomorphic if they have the same number of holes. So this is just circling back to that idea that A topologist is someone who cannot tell a donut from a coffee cup, that there exists some continuous transformation, and what we really mean by that is a homeomorphism that turns that coffee cup into a donut. And what that's doing is reshaping it, and the hole that is in that handle becomes our hole in the donut. Whereas a standard cup without a handle is not homeomorphic to the donut or to the coffee cup. It has no hole that goes all the way straight through. And similarly here, we've got hole, and here we've got no hole. These things cannot be homeomorphic. Some other examples, some things that are homeomorphic. Basically, if we've got like a filled-in disk, then that's homeomorphic to, say, a filled-in square, and it's also homeomorphic to, any closed subset that we call simply connected and has no holes. Any simply connected subset of R2 is going to be homeomorphic to the filled-in disk or the filled-in square. That means there's a homeomorphism between them, a bijection, one-to-one and onto, such that both the function and its inverse are continuous. As another example, if we look at, say, the hollow cube and the hollow sphere, there is a homeomorphism between them. Here's a specific one, f of p for any point on the hollow cube. F of p is going to be p divided by the length of p. That will give us a point on the hollow sphere. And that is a homeomorphism. So here's kind of a famous topological theorem called the Borsuk-Ulam Theorem. So let f be a function mapping Sn, the sphere in R n to n plus 1, to Rn be a continuous function, then there is a point on that sphere such that f of x is equal to f of negative x. So what does that mean? A consequence of that Borsuk-Ulam theorem is that there's no continuous one-to-one function, and therefore also no homeomorphism, from Sn to Rn. But this is stronger than saying there's no homeomorphism, because it's just saying there's no continuous one-to-one function. So we're not restricting that it has to be onto, we're not restricting that it has to have an inverse that's continuous. That's saying, for example, if we were looking at mapping S2 to R2, so S2, that's the hollow sphere, and R2, just the Cartesian plane. Again, it doesn't have to be onto, so we can talk about any subset of R2. Then there's no continuous one-to-one function that maps S2 to R2. So one kind of cute consequences of this is that this is a topological proof that there is no good 2D map of the world. So you've probably seen different map projections. There's the Mercator projection and the Gauss-Kruger projection and all these other ways to map the world onto some two-dimensional space, because two-dimensional spaces are useful, but all of them have some issue. Some of them, the one we're used to, the Mercator, sort of makes things in the northern hemisphere look larger than they are in proportion to things in the southern hemisphere, and so on. So there's all these different projections of maps that are done in different ways that have different properties. But the fact that there is no continuous one-to-one function that takes the globe S2 onto any subset of R2 and onto any two-dimensional subset, no matter how weird we make the projection look, that's telling us that there's not going to be any good 2D map of the world. Another neat topological theorem when we think about continuous functions in Euclidean spaces. So here's the Brower Fixed Point Theorem. every continuous function from a closed ball in R to the n to itself has at least one fixed point. That is, at least one point x such that f of x is equal to x. And this is also true for any space that is homeomorphic to the closed disk in Rn. So, if we're thinking about R2 and like the standard closed disk, that's also homeomorphic to whatever simply connected simply connected subspace of R2 we have. So it's connected and it has no holes, then it's going to be homeomorphic to R2. Could be the closed disk, could be some weird shape that's filled in with no holes, could be a square that's filled in, whatever. So, as an example, say we've got like a piece of paper that's sitting on a desk, and let's crumple it into a ball without ripping it, and put it down right where it was, touching somewhere where it was on that original piece of paper. Then there's at least one point in the crumpled ball that still lies exactly above where it did as a piece of paper lying on the desk. This is this continuous transformation. Turning that piece of paper into a crumpled ball is a homeomorphism. As another example, we said that f has to be continuous, but we're not requiring that f is surjective. So, for example, if you take say a photo of yourself and shrink it and place it on top of your original photo of yourself. So you take a copy of your photo, shrink it, and put it onto another photo of yourself. There will be at least one point where that point is in the exact same location, both in the original photo and in the crumpled photo. So there is some point, x, such that this is f, taking the large photo to the small photo, such that f of x is equal to x. At least one point will be in the exact same location.